To thank the organizers for inviting me to Bangalore. This is a very nice, fine weather away from Chicago. And so my presentation has to do with multi-scale dynamics and multi-scale information. So when I talk about dimensional reduction, I'm talking about scales that are there in a physical system. I will make use of those scales to reduce the dimensions. And then I would like to use filtering theory to find a lower dimensional filter. Then I will use particle methods to solve that filtering equation. This is the roughly three lectures I will talk about. So this is actually joint work with my students, Jung, Nishant, and also Peter Imkeller from Berlin, and Nicholas Pekowski, who's his student from Berlin. So the main objective, let me give you some motivation before I start my lecture. The motivation is to look at data assimilation in high dimensional chaotic systems. So this is sort of what I got into data assimilation problems and climate problems because of Chris Jones in 2007. He invited us to come to MSRI for 6 months, and at that time I got involved in climate issues and climate problems, and that was a starting point of this kind of thinking. So data assimilation, high dimensional chaotic system, it is chaotic, so you have to do a little bit more nudging to the particles than just pure particle filters. So the objectives are to develop efficient methods to assimilate data in high dimensional multi-scale systems. And second objective is to steer the measurement process towards information-rich locations. So I will not talk about that aspect of my research. That has to do with control of sensors. So if you have unmanned aerial vehicles or underwater vehicles, which you can steer to locations, you should be able to take them to places where you have rich information. Therefore, you can use those information in assimilation. So the part I will talk in these 3 lectures has to do with dimensional reduction and nonlinear filtering. So here the dimensional reduction has to do with homogenization. So I will have multi-scale, multi-physics problems. I would like to use homogenization. And I would like to ask the question, how can I homogenize my nonlinear filter? And this is sort of the lectures I'll be giving here. On this part of sensor control won't be a subject of my lectures, but this is an exciting topic that we are looking at. So I will give you a motivation because, of course, I'm in engineering, so most of my motivations come from engineering problems. But for this particular audience, I have, of course, taken the decadal climate prediction as a motivation. So I will have an NCAR climate system model as the starting point to motivate the multi-scale issues that we have in these problems. And main lecture today will be based on dimensional reduction. So this is a typical picture that you see in climate problems. And for those who are in climate science, this is something very common. But you can see there's a large number of nonlinear processes. You have ocean models, you have atmosphere, and you have ice caps, land, and vegetation. And also you have cloud dynamics. And also you have dynamics from outside. These are at different time scales, right? You have resolution, you have different time scales and different dimensions in your space. So this is a typical picture that you see, and because of this picture, you have multi-time scales and also high dimensionality. I think Ramon has talked about high dimensionality as a different kind of high dimensionality. My emphasis here is to ask, so if I want to ask, so if you look at the, put them together as a set of different set of equations, you have ocean model, and depending upon which part of the ocean you are, we are in different time scales. The top part of the ocean is quite fast compared to the bottom. Atmosphere and drivers here are the cloud dynamics, for example. They are at a much faster time scale. And you have sea, land, vegetation. These are, again, this is the kind of time scales you have in these problems. So the standard procedure that everybody has talked about so far has been to look at, this is your typical, you have sensors. Sensors can be from MoCA, it can be from dropsons, drifters, all sorts of sensor information you have. Then you go and look at ensemble carbon filter, 3D-VAR, 4D-VAR, all sorts of things are the data assimilation techniques that we have. And then you want to come and give us some understanding of phenomenon. So for example, it is impossible to start, I would like to ask a question whether we can look at certain phenomena. So ENSO is one phenomena, Atlantic meridional overturning circulation is other phenomena, and you have Pacific decadal oscillation. These are phenomena one can study with smaller models than much bigger models. So what we want to understand is it possible to find these phenomena over a decadal time scales, 10 to 20 years. So with this motivation, I would like to start with the problem of decadal climate prediction. So what do I want to understand is, I will take the North Atlantic because we are in the States. So this is a typical picture you want to look at. I want to find the sea surface temperatures in Atlantic Ocean. And they define, as yesterday somebody was talking about Indian Ocean, a number of hurricanes that are going to be coming out. And also, there's a large number of things about rainfall in sub-Sahara and also in parts of Arizona. Do we have to worry about creating seeds that can withstand a small amount of water? These are the things that policymakers want to know. So as scientists, we would like to advise the policymakers, yes, with a certain amount of probability, it's going to be a smaller amount of rain in these regions. Therefore, you have to go and invest money in creating seeds. This is the kind of stuff the government wants from you. Policymakers want from you some scientifically valid results based on which they can make policies. So this is roughly the problem. So what we usually do is a bottom-up concept. You basically start with a model. The model has large amount of uncertainties. And depending, for example, if you look at, I've given you a typical picture here. Right now, most of the models are about half a degree. I think this is what, that's about 50 to 75 kilometers grid points. And to resolve every fluid dynamics, most of the fluid dynamics, unresolved dynamics, you need to go up to about 1 meter resolution. And that's almost impossible. So the question actually is, you need to parameterize these unmodeled dynamics as stochastic processes. And that is the first stochastic input that you have in a model. So this stochastic parameterization itself is a huge research topic. If you look at Andy Maida and his group in Courant, they have spent a great deal of time trying to find out how do I find the right model to take these unresolved dynamics.
What exactly do you mean by stochastic parameterization?
So the question actually is, you want to find an input that is unmodeled dynamics. For example, if you want to ask the fine scales which I haven't taken, how do I present that fine scale into your model that you have? And so I will come in my next slides trying to explain a little bit more. So, and of course, the second uncertainty comes from initial condition. This is what we have, all of us have talked about. You have initial conditions in these problems. Of course, if you are a climate person 20 years ago, they worked in complete deterministic world. Only thing they didn't know was initial conditions, right? I mean, if you have initial condition and if the system is not chaotic, then, you know, there's no problem. Because system is chaotic in most of the climate problems, and also initial conditions are known, a small errors in initial conditions can give you large amount of errors in the future. So other one actually is the forcing function. The forcing functions are unknown. So there are three primary uncertainties you have in these models. So one has to, this is the stochastic inputs that I have in the system. So the second part is to look from the point of view of data. So you have a model, and then you have this rich data that you have in climate problems, and you want to put them together. It's sort of, this is what exactly data assimilation is. This is what everybody has talked about. Being the last sort of third speaker in the series, I will repeat some of the stuff that people have said, but as Ramon said, it doesn't matter. It's a different perspective. So the observations are aggregated. They are also interpolated. So you can actually see the information you have is you have atmospheric data, you have that all of us have talked about, and you have floats, Argo floats, about 3,000 from what I know, but people have told me here there are more than 3,000 nowadays. And these are the ones that take about temperature and salinity and current data up to about 2 kilometers in the ocean. So the task actually is to take this data and put it into the models and figure out how one can, so this actually I will talk about. So this is so I will start with the first equation here. So this is going to be my model. So now I have a 2 scale instead of having more than 2 scales. I have a Z here. Z represents the atmospheric models. So you have, let's assume you have a PDE, you had a set of differential equations discretized from a PDE to ODE, and you have these, and this is at a very fast scale. Epsilon tells you that is in a faster scale. And in addition to that, you have the unmodeled dynamics that I have there is given by, the question actually is, what is that quantity? It can be, because a simple one will be a white noise. Of course, nobody wants to put a white noise there. So one can ask, how do I define this unmodeled dynamics? Yeah? Because of the fact Z is 1 over epsilon. So Z is at a faster time scale than X. So that is, so I could have many time scales. So if you have more processes, I will have more time scales. But for this lectures, I will just deal with 2. So if you say when epsilon equal to 0, G doesn't move at all, right? That is the time scale. So the question is, what is, so I can actually say d ZT is equal to some x0 ZT So this actually, so this is a model most of us trying to understand. How do I model x0? This is my drift. And so now how many stochastic processes I have to put to create the right kind of a noise I want to put in the model? So for example, if you go back to in the early 2000s, a large amount of work was done to figure out a model for chi0 and chi for these problems. So it is
stochastic parameterization, you want to parameterize the noise part.
Noise part, yeah. there is also other way of parameterization, which I will not consider here.
I guess the question I'm raising is often unmodeled dynamics cannot just be thrown into an additive.
No, it is not necessarily additive. It can be, so the question actually is, how do I take so the way they like to look at this actually is to look at, take the PDEs and look at some sort of a center manifold reduction and try to find the effect of fast dynamics on fast dynamics and try to figure out how to get x0 and xi, or chi0 and chi0. This is the color of the noise. So for the talks, yeah.
I mean, I don't know whether this is a good thing to go into right now. I can also ask later, but is there a principle, I mean, in toy models, is there a principled way of doing such a reduction? Let's say I start with a deterministic system with 2 time scales,
Yeah.
and I do some form of homogenization, I get out a stochastic system.
Yes.
In the principle.
Sure. That's what I'm going to do.
Oh, okay.
Okay. Yeah, this is what I'm going to do, but I think I'm asking the question, how does the noise enter the system? The noise enters the system through unmodeled dynamics. So in the
You think of the unmodeled dynamics maybe being fast time scales, that you're not modeling, right?
yes.
So then you're saying, okay, we just replaced them by noise, and we assume that they're sort of going but I'm wondering whether it's a principled way of a noiseless system.
No, that was the one that was done by Andy Maida in 2000. Try to ask a question, how does one take, if you take a Fourier modes, roughly, so you can actually have a spectral gap, and you will see about maybe 10,000 modes within this spectral gap, and you have this larger modes. The question actually is, how do I find the effects of nonlinearities in the larger, these fast scales? And those were modeled by Andy Maida in a way to represent these noises. So it is not, I'm going to assume in this talk that there is a noise, and the noise can be colored or white. And how do I get the colored noise? I will not talk about it here. This is what you were asking, how to get the colored noise. Okay. So, and yeah. Here it is Chernovich sense. I could have made it into W, because when you talk about modeling the physical process, it was done in a Chernovich sense with the correction has to be to V2. So it doesn't matter here. I'm so used to writing Chernovich, so I didn't think about it. Okay, so you have a model that is given in 2 scales, and you have now observation that I think all the speakers have discussed, from Sajiva to Dan, that this is a observation now, Y, and Y contains both fast and slow signals. And then, of course, VT is a sensor noise. And H is what we call a sensor function, right? So, and this is the setup. So in a much more general sense, you can also have a theta, which is a parameter, and the parameter also can be obtained. So there are 2 problems. The first problem is nonlinear filtering. This is what we've been talking about. This particular problem, where you have phi t epsilon of phi is a test function, and of x and z given the observation up to time t. And this is your conditional law. Okay, the conditional law is what you want to find. And so most of my talk, I'm going to talk about this aspect of this particular problem. So if I have to talk about just x and z, there are no new results. The question I want to ask is, I would like to find the conditional law of x, right? X is your ocean. I'm not interested in atmosphere. So the conditional law of x given all the information up to time t. So the question we want to ask is, if x itself can be homogenized, to x0, does the filter reduce its dimension? And the answer is yes, and you have a lower dimensional filter. So from the higher dimensional system, I have a system that is, I think, m plus n in my signal. I am now trying to find out how to find x, which is just an n-dimensional problem. And for that, I have a low dimensional filter, and that filter is what we will derive. Yeah. Yeah, you can think of this as a, so the homogenization is a very, so the way I would like to look at it from the point of view of martingale problem. This is what we want to do. So we want to ask about tightness of measures in the low dimensional description. And so that is the way I would like to use the homogenization, but it is true, it is some sort of a projection. So to make sure that when you have a gluing, when you have bifurcations in these problems, there are something called gluing conditions. And to do the gluing conditions, you need a bigger hammer. And this bigger hammer is a martingale problem. So I will use that hammer. But if you don't have gluing condition, you can use just simple projections, right? Because when you're taking averaging, when you take averaging over orbits, if the orbits are just periodic orbits, it's no problem. When they go through homoclinic orbits, okay, this takes infinite, then you have to do a boundary layer problem, close the homoclinic orbits. And for that, I need a little bit of a bigger hammer. I won't go through the details, but this is what you can look at the papers. So, and then you have to ask the question, how do I glue the trajectories inside the homoclinic orbit and outside the homoclinic orbit? And that they're called gluing conditions. To get those things right, you need a little bit of a fancy thing. So we will do some sort of a boundary layer analysis. But so you have, so I'm interested in X dynamics, just the ocean. Therefore, you want to combine the homogenization techniques and nonlinear filtering to obtain a low dimensional filtering equation. So the purpose eventually is going to be, so let me just write it here. I didn't. So if you look at what, let me call it pi t, A, this is what all of us have been talking about, x t belonging to some set A, given the information of y up to time t. Right? This is what we want to, x, all right? It is not x and z. So to get this, I will start with x and z. I take a marginal. Marginal will be integrating the z out and showing that converges to the homogenized filter. So my lecture starts now. So this is sort of the first part is to just to get into what we want to do eventually. Z is gone. Z is homogenized. So the atmosphere is going, see the Z is going at a fast rate. The homogenization allows you to remove Z but change my vector field B of the slope. That is like averaging or homogenization. So you have an effective vector field which considers the homogenized effects from the Z. So what happened is the homogenization allows you to reduce the dimension of my state field, vector field. But that is an old problem. But the new problem is, does the filter reduce the dimension? That is what we have shown. All right? So because of the fact that x epsilon goes to x0 is given by a lower dimensional description, then the question is, can the filter be reduced? So what we're going to show actually is, yes, the equation for this filter, so pi is the filter, but you can write this pi in terms of unnormalized density u. And so I think as Rajiva and also Dan may have talked about, the pi is given by Kalyanpur, Kushner-Kalyanpur equations, which are nonlinear PDEs, SPDEs. But Zakai, the equation is for unnormalized density. The unnormalized density is given by a linear SPDE. So we'd like to deal with the linear SPDE. So what we can talk about actually is, so let's assume U is your unnormalized density. So the question actually is, we can show that there is a homogenized U, and that is given by L star, and I will call it dagger here. This is my homogenized. Okay, U dt plus H hat is my averaged sensor function. Okay, which is a function of x multiplied by U, but now I will derive with respect to the complete data. This is the complete data with our epsilon. So this is now the low dimensional filter. So we want to show the convergence of the marginal of the original filter to this, and that is what the theory part of it is. Right? And then we say we have this dimension is much lower than the, so this dimension L of this process is huge. This is about m plus n dimension. L dagger is just n dimension. Right? Therefore, if I want to apply what Ramon and Dan have been talking about particle methods, I would rather apply it here because of the dimensional reduction. Number of particles will be easier. Some sort of thing, something like that. But I want effectively. I'm not throwing out. It's not like, I'm cutting off the bone and I'm being a surgeon, trying to take all the important parts from the part that is going to be cut out. Make sense? Okay. You got a problem? No. No. If no, the whole point actually is, for me, the climate memory is the ocean, the kettle. So the question I would like to ask is, what are the sea surface temperatures, right, in a decadal prediction? The couple system. Oh yeah. Yeah, modeling the ocean, predicting the ocean, right? The reason actually is I have a theoretical result I'm presenting. There's no theoretical results if I want to do filtering in X and Z. There's no theory here. Only when I ask the question, I want to find X, then the theory comes in to show I can reduce the dimension, right? If I want to get X and Z, you go back to standard methods that Dan has been talking about. So it is like, if I'm interested in this ocean, I can actually bring the system to a low dimension and study it. And how do I do it rigorously is what we want to do. All right? So, no, that is Z. So that's something called Dublin condition. We will assume that sufficiently fast that Z has some sort of invariant measure, right? Otherwise, you can't average things out. I mean, in nature, whether you satisfy all these things, we had to figure it out. Maybe Ramon knows it. I do, but it's, yeah. So let's come back to, so this is something, so now this is for those who are not familiar with stochastic differential equation. I didn't know what kind of audience, so this is a standard stochastic differential equation, of course, and you have x is the whole trajectory, right? We will be dealing with martingale problems, so you need sort of canonical space set up. So x is the whole trajectory, and the P of x is a probability measure of x with the initial condition x0 at x. And so we all know that this is SD defines a Markov process xpx, and the correct way to represent that is this integral form that is a Ito integral. So this is where the question was Ito or stochastic came. Of course, we'll deal with Ito, right? So, and whenever you have a Markov process associated with the Markov process, there is a generator. A generator defines a Markov process with a drift and diffusion. This is the standard stuff. And the domain of the generator is C2, twice differentiable in Rn. So this is from a textbook, and we will use Ito lemma all the time. So I just want to define again. So given a function phi, I can define the differential equation for phi using a standard Ito lemma. Oh, yeah, sorry. It's actually, no, phi actually, here is x of t. It should have been c twice differentiable in x. Here, yeah. But, yeah, not for the generator. You're correct. Correct. It's not for the generator. Yeah. So I think it was just a typo there. So generally, you can actually write the, I will use Ito formula here and there. Then one can think of this as a formula I will use throughout some of the derivation I do. So I will actually have, again, I will have this as my symbol, right? And this is defined as Aij, d phi dx, d psi dy. So given phi and psi, and this is your phi, and L of phi is given by this. These are just to make sure all of you have the same notations. So I will start with the classical averaging. This is sort of the standard. It goes back to Hesminski. So this is the first time I have a reduced system, and I will talk about this a little bit more carefully. There's no proofs. I just go through what the results are and show how it can be applied. So I have a vector field, F, n dimension, all right? And the right-hand side is a random process, but it is driven by a process Z, and which we will assume is strongly mixing. So it is to do with ergodic processes, the strongly mixing process. So this process, only assumption is satisfies strong mixing condition. So mixing conditions like weak dependence. Okay, if it is white noise, delta correlated. So this is the first example of classical averaging. The question actually is it possible to reduce this to something simpler? It goes back to Bogolubov and Matropolsky in physics. Those who are from physics, this is averaging theory of Bogolubov and Matropolsky, but in stochastic context, it was done by Hesminski for the first time. So what Hesminski's result tells you is, yes, if, so here I have the expectation of the vector field. MT is the averaging operator, just 1 over t, limit t going to infinity, 0 to t. Okay, that is my averaging operator. So this quantity, if it is not 0, then dx by dt, the x dot, is a deterministic vector field. So even though you have a stochastic vector field, averaged equation is a deterministic process on the time scale of 1 over epsilon. Okay, 1 over epsilon is a time scale on which this approximation is valid. But the beautiful, Huh? Pardon? Oh, yeah. I'm sorry. There's no epsilon. There's no epsilon in this. So this epsilon goes to 0. I'm sorry. There's no epsilon here. There's no epsilon here. Right? In the time scale, 1 over epsilon.
So f bar x bar t, but the right-hand side, how does that determine x bar t?
Right-hand side?
So f bar x bar t equals something.
Yeah.
How does x bar t show up in the right-hand side?
X bar t is actually a bad notation. X bar t is the new average process. So this would have been x bar t on the right. So what this would have been?
Bar is a function of what?
Yeah. This would have been small x and small x.
Okay.
Sorry. So this is a typo here, as Ramon has pointed out. So the right way the right-hand side should be is f bar of small x is equal to mt expected value, oops. Yeah, so it is here, it is a small x, all right? And there's no xt. So that is the way, that is a definition of f bar. Then I replace the small x by xt here. Yeah. So this is sort of, when you do cut and paste, sometimes you don't realize you're cutting and pasting wrong things. Okay. So this is my average system. The average system is deterministic. The difference between the original process and the average process is a Markov process, right? And that is the normalized difference, and it converges. So this is the real. So I take f of x. This is here I've done it right. F of by x, and this is your expectation. This is your covariance. You take minus infinity to infinity with respect to s, and you will get the sigma transpose. This is your diffusion coefficient, and this is your averaging. So this is the way you get f bar. So an averaging operator is defined here, 1 over 2 pi if we have a simple periodic function. So the important result is this. So you average your random dynamical system. The stochastic noise that enters a random dynamical system is strongly mixing. Therefore, the average system is deterministic as long as average is not equal to 0. And the difference between, normalized difference between the original process and the average process converges to a Markov process. And that is defined by, by this equation here. Okay, this is the classical results of assimilation, 1962, before most of you are born here, except for a few people, before most of you born here. Okay, so let me go through this in an intuitive example. Then you can see. I've gone through in a higher dimension, so you can see how it works. Instead of taking the one-dimensional version, I'll take two scales. Z is very fast, and X is slow, right? So I'll just show you the results first, and then I'll go through the calculation a little bit more carefully. So what it tells you is, if you look at intuitively, you can see X is slow, therefore xt is almost like x, small x, right? I can fix X. And then you can see as this is a Ornstein-Uhlenberg process, and this will give you this as a density function. And that is your measure of z for a fixed x. And now you average z here with respect to this particular measure. Therefore, you will get now x dot is equal to b. This is your deterministic equation, right? So a little bit more carefully, I can go through it for those who haven't seen this before. So I fix my x, zt dot. So I go back to this equation here. I fix my x, all right? If I fix my x, I get this equation here. So all of you know particular solution, all right? So if you go and put the particular solution, apply Ito formula for this, just to make things life easy for me. Plug it inside here, I get this equation. Integrate it, you get this. So ZT is this quantity here. All right. So now you can find the expected value of ZT. The W is gone because the Wiener process, so you get expected value of ZT is equal to this quantity here. And this is a variance. Now you Ito isometry for this, you get this. And therefore, the answer is variance is this is my mean. As t going to infinity, I get x here and sigma squared by 2 as the density, normal density with mean x and sigma squared by 2. And that's the reason why I had this as my invariant measure. So if I now go and do the calculations, this is again a simple calculation, you will get x cubed and sigma x. So what I have now, this is my lower dimensional description. Now you can see the picture here. The picture actually is you have z and red, all right? This is my original process. Now you can see the below, this is the, I don't know which one is what. Yeah, so the red one here is a real process and the green one is the average process, right? It's a deterministic and it basically follows. So I can actually effectively use that one-dimensional effective thing. This is a deterministic equation, therefore you can do it in one way. Left the original. I'm putting x and z together.
X is red and blue is
Blue is z. Okay, it is this way.
And the red not only has C, but it has the two.
I'm comparing the red and the effective average.
The very noisy one is X, the one that you're homogenizing.
Yeah, exactly. Right. So this is the kind of stuff I thought this picture will give you an idea. So basically, so I'm asking the question, hey, I can actually use a green one instead of red and blue to get the effective one. Yeah. In the order of 1 over epsilon. If you keep on going, of course, it's going to, on the order of 1 over epsilon, they are close. Right? Okay. But the second theorem is, what if f itself is 0? That is, if you average it, f can be 0. That's called a centering condition. This is real homogenization. Centering condition. So if f is equal to 0, then you will have, according to this particular theorem on 1 over t, x doesn't move much. So what Stepnovich, he was the first one to observe this. It means Stepnovich is one of the brilliant guys, the physicist, but he had fantastic ideas. He basically said, if I wait long enough, if the centering condition is satisfied, if f is equal to 0, if I wait long enough, on a longer time scale, x by itself will be a diffusive process. Right? And that is a result, and I will actually go through this. So this is the Haspinski's result of 66. And here you have a vector field, and you have two processes, and this is your drift, mean drift, and is your diffusion. So now the answer is, I have the resultant equation is not a deterministic equation, it is a diffusive process with sigma and A as two coefficients. This is the second. First one is called advective limit. This one is called a diffusive limit, right? So this is very old. The point actually is what happens in much more fancier problems. So this is where we will sort of get into. So what I was talking about before is, without too much of bells and whistles, you have very nice dynamics, right? So in many problems, especially in engineering, you don't have very nice dynamics. Things are much more complicated. So what you have is, you have homoclinic orbits, which are all over the place in absence of noise, in absence of dissipation. And we'll assume the noise is small and dissipation is small. The core structure is sort of conservative. This is for this particular slides. So you can take a Hamiltonian structure or reversible structure. These have some symmetries. Because of symmetries, you have these nice global pictures. So the problem I'm going to talk about, so we take a very simple equation. You have a Hamiltonian, And the Hamiltonian has this is your potential here, all right? And you can see it has wells and oscillations, rotations, and they are separated by homoclinic orbits. And to this, I would like to add some dissipation, that is my B, and some noise. And I ask the question, is it possible to reduce this system to a low dimension? Right? So the question is, when I reduce, so I have this fast, fortunately, in this particular example, the fast dynamics is deterministic. I could have added noise to it also, but here the fast dynamics is just gradient of a symplectic gradient of my Hamiltonian. Right? Yeah, come on.
This picture you're drawing is the nominal,
This is without the perturbation.
So what is the perturbation?
The perturbation is here, B plus sigma. So you can think of this, or here, we have a,
Perturbation is delta, is gamma H, right? The gradient of H.
that is a core. Perturbation is L.
So what is the fast time scale and what is the slow time scale?
The fast time scale is the Hamiltonian dynamics. This is the fast time scales,
Okay.
right? So actually my fast time, so if I want to go back to the original, so I can, the way a physical system would have been given would be, I will have, say, d of x of t is equal to gradient of h of x of t, order 1, plus epsilon b of x of t plus square root of epsilon of sigma xt dwt. This is the real physical problem that is given to you. If I change my time, so that I'll have 1 over epsilon here. So here, this is a fast, this is slow. So I'm taking a Hamiltonian system and adding a diffusion with a drift. Right? So I have a generator for my perturbations. Make sense? Yeah. So that's what I have. So the question actually is asked, the question, this is of course a two-dimensional problem. Can we reduce this to, yeah.
Gradient bar means
Yeah, I'm sorry. It's called a symplectic, J times gradient, symplectic gradient, sorry, yeah. I'm sorry. Huh? It's a regular perturbation, yeah. Regular perturbation, correct. There's no singularity here. Yeah. So this is the one that is given by L, all right? This one is my L here, right? And this is by 1 over delta. So I think one of the ways to, we know this is actually a Markov process. Okay, this we all of us know. One of the ways to characterize the Markov process is through martingale problem. So one can show, this particular, so if we take, so I want to go to the canonical space, I take xt being the coordinate function. So if you go, you have to do all these things to apply properly the martingale problem. So one can show this is equal to 0. This is like the sigma algebra up to s time s. So I take t, mt minus ms will give you this. So the purpose is to ask, is it possible to find a Markov process for h by itself? We know h and x are coupled together. But h by itself is on a Markov process. And we want to show, yes, h by itself can be a Markov process as epsilon goes to 0. But this will be given on a graph-valued process because I have its homoclinic orbits. Exactly. Correct. So the h is correct. The h is, so what you have here is you can see h dot is equal to 0 without perturbation, right? I mean, if I write here, so dh is going to be equal to, what's going to happen is this part will be gone. Okay, you'll be having here a gradient of h, comma, symplectic gradient of h, that is 0. Therefore, I will only have epsilon. So H is slowly varying. X is fast. All right, this is what we want to do. So as Ramon said, I will now, even though I worked with this particular problem, I have brought it into a singular perturbation. I have this is slow varying, this is fast varying, right? And therefore, I would like to ask whether H by itself is so what we have to do is, so initially, this problem is given in R2. But now I would like to create a new space. This particular space is basically a quotient space. I have an equivalence class, all trajectories of the same energy level, one trajectory is one point. So for example, if here this one, okay, let's take 2. 2 is the well inside, 3 is a well here, and outside the well is 1. So all points here, which is goes around this orbit, is one particular point. They call equivalence class. So what we can do actually is I have now a new state space, and this state space is tau, gamma. Gamma is R2 quotient. It's a quotient space roughly. And this vertex here corresponds to the homoclinic orbit. Right? So you can, so let me take a picture here. This is sort of a, so I have my typical picture I have is this. So this is my state space. Call this one x1, x2. So now I have this is my R2. My martingale problem is defined in this particular space. So I have here a space of continuous function from 0 to infinity, and I will kill the process here. I don't want to go to, I'll just kill the process. So I'll use kill martingale. So I'll just stop it here, right? Otherwise it keeps on going. So the question actually is it possible to find a lower dimensional? Because this is one dimension, I can go and solve it by hand. I can't solve this in 2 dimensions by hand. This is completely impossible. In 1 dimension, if I can reduce it to 1 dimension, I can glue them, I can solve the complete expression for your invariant measure. So what we show is that indeed I don't want to go through this, just leave it. So let me, the results are missing. So what we have, what we can show actually is, so one can show that the generator on this is given by L H dagger. It's going to be equal to this quantity, and this quantity. I have to average now the x. X has to be taken out of this by the averaging process. So this is actually in 2 dimension to 1 dimension. Now if I now take it to a higher dimension, this actually is a little bit more complicated problem. Here you are talking about waves under jitter. It is a NASA project. And what we have actually is a set of conservation of mass for the correct. So now, correct. So I have now the martingale problem is defined in 0 to infinity gamma in this space. So I basically show that there is a generator as a problem. So you're going to go tightness of measures in this space and show there is a limiting cluster point, and then that solves a martingale problem. And therefore, I will have a lower dimensional generator with a gluing condition. I'll come to that in this bigger example. So I'm going to just go with the same structure to this particular example. So at this particular point, yes. So I'm going to flip a coin. So I'll be going this way. So I'll show it. Okay. I'll be going here. Of course, it's one-dimensional diffusion. I keep on going this way. When I come here, the gluing condition tells you there's roughly a three-sided coin I'll flip. Okay, and depending on the flip, I'll decide whether to come back, go out, and the coins are not equal because depending upon how the dynamics of these, they don't have the same probability, right? So it will decide at the vertex whether to go to 1, 3, or 2, and that is the gluing condition.
The vertex have to do with the worthiness of the saddle?
No.
I guess I'm coming from your point of view. You have a
So,
saddle and an index.
yeah, here I think the way we are looking at actually is, so we stop here and do a boundary layer about this particular point. And then we have to use something called Heskinski angles to figure. So it's actually a long process. In fact, the papers are long to prove all these things, but the results are elegant. So results basically, so I can show you in this example, it's a bit hard, it's a harder problem, so you can see how the picture looks like. Okay.
For this kind of simple problem, if you, is it attaining numerical results on this full,
Yeah. So
the complete dynamics?
the complete dynamic.
Can you see this happening?
So what we have shown.
Because the period goes to infinity at the.
Sure. That's the reason why you had a gluing condition. You can't average all the way to the vertex. So you have to stop somewhere nearby and then glue these things properly, right? That's the whole. So in fact, we have also doing filtering on this. So this is eventually we'll show you what we are doing. So this part of the lecture is to look at lower dimensional problems. So high dimensional problems, I can bring to lower dimension, right? So do you have a, yeah.
But here you started with the one-dimensional, sorry, you started with
Two dimension
and what you reduced to
is,
not a subscript. Originally you said you have
Correct.
x and z and now you want to write
Yeah,
something for x and z.
sure. That's a good question, I think. Yeah. So in the first problem, in the first problem, there was no bifurcations, right? There's no homoclonic. That's the whole point. In the ocean and atmospheric problem, I'm assuming there are no bifurcations of the kind where you can use it. So if you have smaller problem where you have real bifurcations, there also you can use it. So here you need this martingale approach to do the problem. Make sense? So if you have bifurcations, this is what we have to do. But there are maybe other ways to find the low dimension. So here you can see I have two modes, which mean four-dimensional system. So I'll come back to this. So I have a Q and P. It is a two-mode wave equation. So you have four-dimensional system. I add white noise and artificially add dissipation. Okay, viscosity was removed and then added on later on, right, to get the right structure. It goes back to the work of Miles, J.W. Miles in 1984 without the noise. He added periodic perturbations and we added stochastic processes here. So what you have actually is in four dimension, right? This is two dimensions. The four dimension, I have a Markov martingale problem. It's a Markov process satisfies the martingale problem. So the question we want to ask is, same way I want to reduce so here I will reduce a space. Instead of having just lines, I will have these planes. One plane, other plane, another plane. So now each plane is a two-dimensional problem which is glued together at the vertex. Okay? So now I have two conserved quantities, h, and one more quantity I. And then the question actually is it possible to find the low?
So the original system
Is four-dimension.
is four-dimensional, but
Yeah. So the question actually, yeah, integrable, correct. because you have 4 dimensions, you need 2 constants of motion,
You have H and I.
H and I. So because of which I could show that I can bring the dimension to 2. Yeah. So now my system went from the law of the Z, which is 2 dimension, is given. So the whole point of martingale problem is to identify this L dagger and try to find B's and Aij and the gluing condition. The gluing conditions are like this. So looks like the, so now look at the domain of the operator. So F is continuous in the whole stratified space, twice differentiable in the open intervals. The limits work, and this is the condition at the vertex. It basically tells you, I will come here, I'll be doing a 2-dimensional diffusion. I get here, then I flip a coin according to this particular law and decide where I'm going to go. So this is a reduction, and this is the description of the gluing condition. Heuristically, you can think of as a coin flipping, right? So the main result is the P epsilons, that is so martingale problem works on probability measures on canonical spaces, right? So basically we say this one converges to P dagger, there is a cluster point, and that solves the martingale problem on this stratified space. The domain of the generator is given by D bagger, and that I explained before. So in summary, we went from a 2-dimension to a lower dimension which we can solve, right? And this is sort of the summary of reduction, the 4-dimension, yeah, which you can solve. So it is actually in weak convergence, so it is only in distributions. So if I want to look at distribution, so it is not you can't talk about trajectories, right? So in the starting from next lecture, I will basically work with this equation, which is my homogenized equation, and try to show that I can define a filter for this. So today's lecture has to do with dimensional reduction, homogenization, averaging, and this will be the key in the next lecture in developing nonlinear filters.
Observations will depend on both the fast and slow.
Observation, Y will depend on all of them. I won't average my observation, but I will average the sensor function at certain points, but they're driven by the real observation. So here, that's the important part. Okay, so, okay, I'll stop here and then, yeah.
Define this distribution of it. What do you lose?
I mean, these are all, okay, these are only at the scales of 1 over epsilon squared. So it is only for a time interval of 1 over epsilon squared. So beyond that, one cannot say too much about this, right? So it is an approximation.
If your average function is not 0, then it's valid for 1 over epsilon.
If
it is 0,
advective. If it is advective, the average function is deterministic.
yeah.
Okay?
But then it's valid only for times 1 over epsilon. But in this case, it is valid for 2 times 1 over epsilon squared.
No, I think, so that was actually not true. I think usually we put here this one and that one, all right? Epsilon square in both, same in both cases. I'm sorry. Same in both cases. Yeah. Correct. One is without centering condition, other one is with centering condition. That's all. Yeah. I'll stop here. And any questions? Yeah.
So you've given a homogenization procedure for equations without conditions, right? So in principle, if I have a filtering model with underlying model and the observation, I can view this jointly as an SDE, right? And I can apply the homogenization to this, find a homogenized SDE for the joint system and observations, right?
Yeah, what I want to do actually is, yeah.
The question is, so now if I'm a physicist, right, and I say, well, so now I'm going to filter, so now I'm just going to run the filter for the homogenized system observation pair. And of course, there is something to be done to make that precise. But is that correct, or is that actually is it actually different? Is it not what you expect? What's the final answer?
So the question is, what is your filter equation is?
Is the filter equation, the homogenized filter equation, going to be the filtering equation corresponding to the homogenized underlying system?
Not really.
No. So you're going to get something unexpected.
Unexpected. Something there which is actually going to be there. So I'm going to be driving the system by the real noise, real observation, and the generator will be a homogenized generator. That L dagger will be a homogenized generator. But the Y is the real observation. Make sense? Pardon?
I mean, there are two ways to go, right? To homogenize the original dynamical system, stochastic dynamical system, and then derive a filter for that.
That's the way we started. No. So the way we started was we said, okay, as intuitively, what will you do is you go and homogenize my system. All right? And then I said, okay, for this, I have a new filter. Does this converge? But there you will have Y0. That is my averaged. But we don't want the Y0. We want Y epsilon.
But they're typically continuous in Y. Right?
They are continuous in Y. Therefore, that's the whole point. Then because they're continuous in Y, I could replace Y0 by Y epsilon. So that is roughly.
Okay, but the filter is still the filter for the homogenized system.
Oh, yeah. So, of course. All for the homogenized
Sometimes
purpose.
there are surprises, right? But recently,
No.
in e-literature, discussed in e-literature, there have been surprises.
I see. I don't know that. I should talk to you about it. Okay. This is only for the homogenized. Yeah. So what we have shown actually is, if I now go back and do Monte Carlo for the coupled system and look at the filtering of the slow process, they're exactly the same. So there's no, first we show it rigorously and then show numerically. Yeah. So
I guess in optimal control theory,
separability,
the question rose whether you should
separability of,
whether you should sort of discretize, do the control, optimal control theory at the continuous level and then discretize, or whether you should discretize.
and then
The answer is
they don't commute. But here also,
and could lead to
yeah, that is called spillover effects. In addition to that, yeah, spillovers is one of the things.
the way the
Okay. But here I think we didn't come across this because we started with ODEs, right? So.
Okay, so this is thanks, Sri.
Yeah.